Let's see how the sine and cosine functions are related to the unit circle. So here we have quadrant 1 of the unit circle. You can see that we have chosen a point that lies on the circumference of the circle, and we're going to call that point P. And the coordinates of that point P are A, B. So the x coordinate is A and the y coordinate is B. Now, if we consider the right angle triangle that this forms, so there's the radius, and then we know that if we're at point AB, that this length will be A and this length here will be B. That's formed a right angle triangle. Now, if we recall our trigonometric ratios, so we know that cos theta is equal to the adjacent side over the hypotenuse. So if this is our angle theta, then our adjacent side is A and our hypotenuse is 1. So you can see that cos theta is actually equal to A, which is a little bit interesting. Now, if we think about sine theta, which is opposite over hypotenuse, so it's going to be B over 1, then you can see that sine of theta is equal to B. And basically what that means is we've just shown that, well, for this right angle triangle, that our value A is going to be equal to cos theta, and our value B is going to be equal to sine theta. So in general, we can say for a point anywhere on the unit circle that the x coordinate is given by cos of theta, and the y coordinate is given by sine of theta. So this becomes really useful because when we have certain angles, we can work out what the coordinates of certain points anywhere along the circumference of the unit circle. If we consider tan theta, we know that tan of theta is opposite over adjacent. So looking at the opposite length over the adjacent length, which is b over a. So what did we just say? We just said that b was equal to sine theta and a is equal to cos theta. So tan theta can be written as sine theta over cos theta, which is another useful property. So as I mentioned, now that we know that any point along on the circumference of the unit circle can be found if we know an angle using the x coordinates given by cos of the angle and sine the y coordinates given by sine of the angle. So here we have an angle of 75 degrees. So at 75 degrees, I can find what the coordinates of that point would be by finding the cosine of 75 and the sine of 75. And we can do that for any angle on the unit circle. So we could also do it with some negative angles as shown here. So we could consider the positive angle being 327. So at that point, the x coordinate would be cos of 327 and the y coordinate would be sine of 327. Or alternatively, we could use the negative angle and we could just do cos of negative 33 or sine of negative. In the first video, you would recall that we spoke about the equation of the unit circle being x squared plus y squared is equal to 1, and we looked at a number of the factors which influence the equation of the circle. Now, we can expand on this because we just said that any x coordinate could be labelled as cos theta, and any y coordinate on the unit circle could be labelled as sine theta. So this shows that another useful property which we'll use in the next year or so, that cos squared of theta plus sine squared of theta is equal to 1. Now, for all points of the unit circle, we consider the x values between -1 and 1, and we consider y values between 1 and -1. Because that purely just comes from the definition of the unit circle, because we know that we're dealing with a circle with a radius of 1, therefore we're not dealing with any y values which are going to be greater than 1, and we're not going to be dealing with any x values that are greater than 1. And because we've just shown that the x coordinate can be shown as cos theta, then we can say the same. So the values of cos theta have to be within that range, and the values of sine theta have to also be within that range. So all values of cos theta will be between -1 inclusive and 1 inclusive, and between greater than or equal to, the values of sine theta will be greater than or equal to -1 and less than or equal to 1. Let's consider the definition of the tangent. So here's our unit circle. We've drawn a tangent at the point 1, 0, and we've also extended the line OP, so it was the radius, but now we've extended it so it reaches the point at the tangent. Now, this position of point Q, where that radius which has been extended intersects with the tangent, relative to this point A, is what is defined as the tangent function. Now, you can see that in this diagram, we actually have two right angled triangles. We have the smaller triangle OMP and the larger triangle OAQ. And what we know about those two triangles is that they're equiangular, which means that all three of their angles are equal. And we could show that because those angles are 90, then we have two parallel lines, therefore the other angles are equal, and then they share that angle there. So when we have two equiangular triangles, it means that they're in fact similar triangles. And when we have two similar triangles, we know that the ratios of their equivalent sides are the same. So using that definition, basically what they say is that AQ, which is this length here, over OA, which is this length here, is equal to NP over ON. So those ratios of side, those two ratios are equal, and therefore we can come up with a definition of the tangent where tan theta is equal to sine theta over cos theta. We can also consider tan theta to be the gradient of OP, so the rise over the run sine theta over cos theta. So we've got a little investigation here where we're just looking at the tangent function, and we'll have a look at where it's positive and where it's negative. So this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So you can see my value for P in quadrant 1. So at the moment, anywhere in this quadrant, both the sine value and the cos values are positive. Therefore, the tangent value will also be positive. What happens if I move into this quadrant? Okay, well now all my x values, which equate to the cosine, are negative, but all my sine values are still positive. But because I have the negative values and the positive values, obviously a negative divided by a positive is going to give me a negative, so it means that we are going to have a negative value for our tangent function. If we move into the third quadrant where both sine and cos are negative, our tangent value becomes positive because the division of two negative numbers will give me a positive number. And then finally, in the fourth quadrant, again, we have one value being cos, which is positive, and then the sine values, which are negative. When we do a division of a negative and a positive, we get a negative. So you can see what the values, whether we have positive or negative values for each of those functions in the four quadrants. So in quadrant 1, we have positive for all of sine, cos, and tan. In quadrant 2, we've got positive sine values or y values, but negative x values, which meant we had negative tan values. In quadrant 3, we have negative sine values, which are the y values, negative x values. Because we're doing the division of two negative values, the tangent becomes positive. And then finally, in the fourth quadrant, where we have negative sine values but positive cos values, then the tan is going to be negative. So in that little investigation, we should have discovered that sine, cos, and tan theta are all positive in quadrant 1. Only sine is positive in quadrant 2. Only tan is positive in quadrant 3. And only cos is positive in quadrant 4. And they come up with a bit of a mnemonic for you to remember that. All silly turtles crawl. So all of them are positive in quadrant 1. Only sine values are positive in quadrant 2, only tan values are positive in quadrant 3, and only the cos values are positive in quadrant 4.